All right then. So this is Wednesday, May the 5th, lecture 26, I think. And we're 2 lectures from the end of the class. And this is the last lecture. The last 2 lectures I will be putting online on YouTube as usual. And I'll record those and I'll just let you know when I posted them. I'll try to post them in the next day or 2. Okay, so what we're looking at now is the instability of the steady state. So let's get started with that. So our goal in this section is the following. We have a uniform steady state that conducts heat by diffusion and no spatial patterns are present. So now what we want to ask is what happens if we now make a perturbation of this state. And in particular, what we're going to ask is what happens if that perturbation is a small perturbation. And so we can study the effect of that by linearizing the nonlinear equations of motion. So we're going to require that this be a small, literally infinitesimal perturbation. And what that means is that we can linearize the nonlinear equations of motion. So what we talked about last time, and you can still see it on the screen on the left here, is we did the similar sort of thing in the Landau theory. So in Landau theory, the way we could detect this was measure the susceptibility of the trivial magnetization psi equals 0 state. And as you can see over on the left, if you are above TC, then the state is stable, meaning that if I start over here and then make a small perturbation, so that gets me up to here, then the system is then going to lower its energy by coming back down. On the other hand, if I'm on the right-hand picture, then what's going to happen is that any small perturbation is going to move away from the psi equals 0 state, and so we call that instability. Okay, so that's kind of trivial and obvious. So what do we expect will happen? So we're going to just say some terminology. So if the time evolution of a small perturbation grows, then we see that the state we are perturbing around is linearly stable. And it's important to say linear. Okay. So if the perturbation does not grow, what I wrote down here was complete nonsense. I hope somebody noticed that. What I meant to say was unstable, okay? So let's go back. If the perturbation does not grow, then we say the state is linearly stable. Okay, so now the thing is that what you need to understand is that this doesn't necessarily mean, just because you're linearly stable does not mean that you're actually stable. So a state that is linearly stable, that state may be non-linearly stable. And so what that means is I make a small perturbation, I'm stable. If I make a large perturbation, then I become unstable. And so we'll call that a nonlinear stability. And if that's going to happen, that means that I have to go to higher orders in perturbation theory than just the linear one. Okay, so that's the first thing. Now, the other thing that can happen is that a state that is linearly stable, linearly unstable, well, what can happen is that the perturbation will grow out of the regime of validity of the linear perturbation theory. So perturbation will grow until it is large enough that the linear perturbation theory is not valid. And so, once the linear approximation breaks down, then you can't say anything at all. Now, what do you expect to have happen then is that the higher order nonlinearities can restabilize the solution. Higher order nonlinearities can restabilize the solution. And I've left this picture up on the left-hand side because I want to show you that it actually happens in Landau theory. It's something that you've seen before. So if we go and look over here on the left, so what do you see happening? Well, in linear stability theory, we start off at the top of this little hill in the middle. You make a small perturbation, and that perturbation grows, meaning the system moves further away from psi equals 0. But then later on, the system approaches, let's say, the one on the right, this minimum here. And once you're at this minimum here on the left, or sorry, on the right, then of course, it now becomes restabilized. And eventually, of course, it becomes, it goes to that equilibrium solution. But the only way that is happening is through the nonlinearities. And so that's the nonlinearities in Landau theory. that cause the system to be restabilized. So it's restabilized by the nonlinearities. Well, I'm not going to say nonlinearities because that would be an equation of motion type of statement. And what I really want to say is it's restabilized by the size for fourth terms in the Landau free energy. Okay, and so we know that that's true because if we write down our Landau free energy, and I'm just going to not write down the gradient terms, just look at the uniform terms. So if I write it down like this, then what we know is that for R naught less than 0, the psi equals 0 state is unstable. And eventually what happens is the system evolves to the state psi is plus or minus R naught over U naught to the 1/2. And this U naught comes in down here in the denominator, and that U naught is the coefficient of the size for fourth term. So this is exactly what we've seen in Landau theory, just in equilibrium. Okay, so that's all pretty easy. So now let's return to the convection example. So let's leave that up there. So what we're going to do is we're going to say that the temperature field now is equal to the equilibrium T naught of Z, which we saw as a linear varying temperature, plus a perturbation, which I will write as T1. I will write that the density is rho naught of Z plus a perturbation rho 1. The pressure is P naught of Z plus P1, and then the velocity field is 0, meaning it's at rest, plus a perturbation, which I'll write as U1. So all of these are steady state quantities we calculated last time, and then what we are going to do is we're going to take the equations of motion and we're going to simply substitute in and expand to first order in the perturbations. Okay, so let me write down what the result is. So when you go ahead and do that, what you find is this. You find that rho 1 is equal to minus alpha rho bar T1. You find that div of U1 is equal to 0. That's incompressibility. You find that rho naught of Z d by dt of U1 is equal to minus grad P1 plus eta del squared U1 plus rho 1 G, the gravitational field. And you find that d by dt of T1 plus W1 dt naught by dz is equal to kappa del squared T1. And here, what I've done is I've written the velocity field in its x, y, and z components as u, v, and w. And so W1 in the dt by dt1 equation, W1 is just the z component of the perturbation of the velocity. Okay, so that's the equations. So now I want to we can go ahead and do this, but it's much more straightforward if we actually just kind of review the general strategy. So next, let's review the general formalism. Right, I'm glad our library was prepared for a faster experience. Okay, so let's suppose that we have some field psi, which could be many components as a function of space and time. So I'm going to write that as it's got some evolution equation, which looks something like this. So n is meant to be some spatial dependent nonlinear operator. Okay, so something like this. So then the steady state solution which I'll write as psi naught of x, but then that just obeys d psi by dt is equal to 0, and so that means that it's the solution of n of psi naught of x is equal to 0. So now let's write down some perturbation. So we're going to say that psi is now psi naught of x plus psi 1 of x and t. And then the equation of motion for psi 1 is going to be the nonlinear operator acting on psi naught plus psi 1. And that's going to be, we're going to write that down by expansion. So this is going to be the nonlinear operator acting on psi naught plus dn by d psi evaluated at psi naught acting on the function psi 1 of x and t. And this dn by d psi is kind of like a functional derivative or Fauché derivative. It's just the derivative of this nonlinear operator. So I'm going to just write it down in this way, assuming that you understand what it means. And so I'm going to define this to be a linear operator L acting on psi 1 of x and t. Okay, so what we have now to solve is a linear problem, and in fact, this structure can have all sorts of interesting properties depending on what the system is. So I'm not going to go through what properties L may or may not have. It need not be a symmetric operator. It may, there's all sorts of complications that go on, especially in pattern forming systems, and I'm not going to talk about those for now. Okay, so now let's talk about what happens when we start to look at the stability. So when we look at stability, what we try to do is we say, let's write down psi 1 as some amplitude times e to the I k dot x plus omega kt. So we're going to, the amplitude A doesn't matter because we've got a linear operator here, so that doesn't matter. And then what we're going to try to find out is what the dispersion relation is. So we'll call this a dispersion relation like we did before. And so we want to find out what this dispersion relation is as a function of k. So Now we substitute this into the equation of motion, and so this satisfies omega k psi 1 is equal to L psi 1, the linear operator acting on psi 1. And so what we've learned from this is that the growth rate of the perturbation, so that is proportional to e to the omega t, but it's really omega of k times t, so it's going to be wave number dependent. Let me write this a bit more clearly. So that is going to be given by the eigenvalue spectrum of the linear operator.
When the omega is purely imaginary, does that just means that it does not grow, or?
That's right. So in other words, the growth, if the thing is going to grow, what that means is that omega has to have a positive real part. So that's exactly what I'm going to talk about now, which is look at the following scenarios. So the first scenario that I want to talk about is the case where the real part of omega of k is less than 0 for all k. Okay, so that's scenario number 1. So what that says is I take any Fourier component of the perturbation, and that's going to exponentially decrease in amplitude. So any Fourier component will decrease in amplitude. And that means that the state psi naught of x, the state that we're perturbing about, is linearly stable. Okay, so that's easy. Another possibility that could happen is that the real part of omega of k might be greater than 0, at least for k1 is less than k is less than k2. So what's going to happen is that we'll have something like this. And then these modes in here, these modes are going to be linearly unstable. So they will grow exponentially. And in fact, the fastest mode is the one that's going to grow the fastest. And so because it's going to be the fastest growing mode, it will have some wave number, I don't know what I'm going to call it later, k0. It'll have some wave number k0, and so you might expect that wave number k0 will set the scale for the pattern. So we can say that, so what we can say is that psi will grow until the neglect of order psi1 squared is no longer justified. And the pattern may form predominantly around the fastest growing mode, and be restabilized by nonlinearities. Okay, and then there's another case that can happen. So, well, there's many other cases that can happen. We may have the situation where the real part of omega of k is not strictly less than 0, but let's say is less than or equal to 0. And so what happens here then is that you have a marginal mode with omega equals 0. And so what that means is then is that your differential equation doesn't have this linear term, omega psi 1. And so what that means then is that you have to, it means you cannot neglect order psi 1 squared. And so that means that you have to look at the nonlinear stability. So we're not going to be talking too much about that. Now the situation that I've just described looks something like this. So here I have k, here I have the real part of omega of k, and what I've described is a situation where you may have something like this. That would be situation number 1, and I should point out that this is 0 over here. So I may have that situation. Then I may have a situation where, as I change some control parameter, I now get to this picture like this. So this would be epsilon equals epsilon c, and the blue one would be epsilon being less than epsilon c. And then lastly, we'd have the one that I showed you before, where now you have something like this. This would be k2, this would be k1, and this would be epsilon greater than this control parameter. And so that's what we would expect. Now, what will happen is if we are near the threshold of instability, so what that means is that epsilon is just slightly above whatever is the critical value, then this band of unstable wave vectors, a great name for a physics rock group. So this band of unstable wave vectors will be small, which means if I look at the magnitude of K1 minus K2, as long as that is much less than K0, then we can say that the emergent state will have a pattern whose wavelength is going to be lambda is equal to 2 pi over k0, because that's going to be the fastest growing mode. And so basically the idea is that a random initial condition will amplify the modes of wave number k, and the mode where omega k naught is a maximum will be the selected one, because it will grow faster. Okay, so that's the basic idea. So the basic idea of linear stability analysis is simple, but the execution is often hard. So what we're going to do now is we're going to go back to our linearized equations of motion, and we're going to do the calculation. And I don't want you to really worry too much about the algebra. I want you to just make sure that you understand, roughly what I'm doing. So the next thing we're going to do is we're going to apply this formalism to the convection problem. And the strategy I'm going to do is we're going to do multiple steps, which were cleverly designed to beat the problem down into its simplest form. So multiple steps, and the goal of these is to write the system of equations in terms of one variable. So you could just say, well, just take your system of equations that we wrote down a few minutes ago, stick them on the computer, and many times that's the only thing you can do. But in this particular case, we can do a lot better. So it's now going to be fairly boring for the next couple of minutes. I'm just going to show you some of the manipulations so that you can get some flavor of how one does this kind of calculation in practice. Okay, so let me try to make it as transparent as possible. So the first thing I'm going to try to do is get an equation for the variable W1, which was the velocity field in the z direction. So remember that the fluid is at rest in steady state. And so if the fluid starts to move, well, then that will be an indicator that we're having convection going on. And so we want to understand what equation that would satisfy. So let's start off with our equation rho naught d by dt of u1 is equal to minus grad p1 plus eta del squared u1 plus rho 1 g. So that was the equation that we started with. And now what I'm going to do is I'm going to take the curl of this equation and when I do that, what I'm going to get is this d by dt minus nu del squared. So that operator acting on curl view 1, and that's going to equal minus alpha grad T1 grad T1 cross G. Yes, exactly. Okay, so let me just say what I mean here. So this variable nu is this is eta over rho naught. So what I've done is I bring the diffusion operator over to the left-hand side. So we have that. And then where did this this grad T1 and so on, where did that come from? That confused me. So that came from the fact that rho 1 is equal to minus alpha rho bar of T1. And I'm assuming that this rho naught is what I've called this reference density rho bar. Okay, so that's just some big mess. So we can get rid of this mess a little bit by taking another curl. Okay. So we did this first curl, but why did we do this first curl? Well, what we wanted to do was we knew that if we took a curl, we would get rid of this term over here, and because curl of grad is 0. So now we're going to do the same thing. So we're going to take another curl. So that's going to give us this equation: d by dt minus nu del squared. Now acting, so curl. So I've got two curls, one curl already on U1. Now I take a second curl. So curl of curl is the gradient of the divergence minus del squared. So then because I've got the incompressibility, then that's going to just give me del squared. So this is just going to give me del squared U1. And then on the right-hand side, I have alpha, the expansion coefficient. And now I've got curl acting on grad T1 cross G. And so that gives you G dot grad acting on grad T1 minus G del squared T. And so let me just annotate this. So this came about because curl of U1 is equal to grad div U1 minus del squared U1. So that's just a vector identity. And so now what we have is is this equation up at the top here, where it's a lot simpler. Now, then the other thing that we know is that the vector G is just 0, 0, minus G. It's just in the Z direction. And so what that means is that basically every term here is not interesting except for the Z direction term. And so now we get that d by dt minus nu del squared acting on del squared, the Z component of the velocity, which is then W1, that is equal to alpha times G. And now I'm going to look at the Z component of what's in the square brackets. And so that is equal to minus d2 T1 by dz squared plus d2 by dx squared plus d2 by dy squared plus d2 by dz squared, all acting on T1. Like so. And so, of course, what's going to happen is that we're going to get this cancellation between this term and this term over here. And so what we end up with is just simply alpha G times the perpendicular Laplacian, which I'll write as del perpendicular squared, and then this thing is just equal to dx squared plus dy squared. And so we have simply that simple operator. Okay, so this is great. So basically what I've just shown you is that now we have an equation for W1 in terms of T1. Okay, so we've done that, that's great. But what we actually want is we want to beat this down into a single equation. So let's just go back and look at our governing equations if I can find them. So here they are. So now the idea is I've got an equation for W, and it involves T1, and I've also got this other equation for W in terms of T1, which is this equation over here on the left. I haven't used that equation yet. So now the next thing that we're going to do is we're going to use that equation. So next, what we want to do is eliminate T1 and so get an equation just involving W. So the way that we're going to do that is we're going to take this equation and we're going to operate on this with the diffusion operator. Let me go back to, let me just make sure that you see what I'm talking about here. So if I look here on the left-hand side, so I can write this equation on the left-hand side as the diffusion operator, which is d by dt minus kappa del squared, acting on W1 and then some function of z or some constant. So that tells me what that tells me how W1 is related to T1. In a sense, you can say that the diffusion operator acting on T1 gives you W. So W is just the diffusion operator acting on T1. So I have T1 on the right-hand side over here. And so what I'd like to do is get rid of that T1 by operating on it with the diffusion operator from the equation on the left. So let me just write that down. So since we know that d by dt minus kappa del squared of T1 is equal to minus W1 dt naught by dz. So therefore that says I've got this factor of T1 here on the right hand side, which I want to get rid of. So basically the best way to do that is just take this diffusion operator over here and operate with this onto this equation. That will go through onto the right hand side, hit this T1 and turn it into something that involves W1. So that's the strategy. So let's go ahead now and let's go ahead and do that. So now what I'm going to do is just simply write down what I get. Okay, so we're going to have d by dt minus nu del squared, acting now on the equation that I already had, which is sorry, this should be a kappa. Then d by dt of nu del squared. So now that's going to operate on the object on the left-hand side, which was del squared W1. And now when this operates, when this operator acts on the perpendicular derivative, the perpendicular Laplacian of T1, all I'm going to get over here is minus alpha g dt naught by dz times d perpendicular squared acting on W1. So this is great because now I've got a nice equation for W1. Now I say it's nice, but you might not agree with that because it's a how many derivatives are there? Well, there's 1, to 3 Laplacians on the left-hand side. So we've got a 6th order partial differential equation, but it's linear. But it's linear, and so so we can do something with it. Okay, so that's the first thing, and the other thing I want to point out is that this equation is rotationally covariant. In the xy plane, as you might have expected it would be, just from the physics, but we can see that explicitly because of the perpendicular Laplacian. Okay, so that's the end of step 1. So now let's go to step 2. So now I've got a linearized equation. What I need to do is find its eigenvalues. So you're used to finding the eigenvalues of an equation like the Schrödinger equation. Here we have an equation that's much more complicated than the Schrödinger equation. So let's see if we can work it out. Now, the way we're going to do this is pretty much the same way that we solve the Schrödinger equation, which is to use the separation of variables. So the method that we're going to use the separation of variables, and so what we're going to assume is that the w of x and t can be written down as some function which I'll call capital W in the z direction times some function in the xy plane, and then e to the omega t. So that's what that's a way of writing down the separation of variables. Now, for reasons that will become clear as I go through the calculation, we're going to want to put a constraint on this function f of xy, just like we usually do when we have separation of variables. And so I'm going to insist that when I operate with the perpendicular Laplacian acting on f of x and y, then that gives me just some number which I'm going to call a squared times f. So this is going to be a kind of subsidiary eigenvalue equation for the function f. Excuse me, 1 second. Let's resume. So so a is going to be some constant. Now, why do we do that? So remember that the basic idea of separation of variables is that you get some function, let's say of z, and that is equal to some function of x and y. And then if that happens, then that implies, once you get that condition, that then implies that both the left-hand side and the right-hand side must be constants, even though they seem to be functions of x and y and z and so on. They must be a constant and they must be the same constant. And if that's the case, then that's how we use it to simplify the problem. So I'm going to insist on that. And then once I do that, then I can now substitute into the equation and find out what I get for my function w. So let me write it down because it's a mess. So what we get is this. Okay, so this is what I get. Now, what is this capital D? When I write down capital D, that just means d by dz. And so this looks great. Now I've got an ordinary differential equation. And somehow we have to determine this quantity A, and we have to determine the eigenvalues W omega. Okay, so the things that are still very much unknown in this equation. So we want to determine these are the eigenvalues, and we also need to determine A itself, because that is also some kind of eigenvalue, and there's one over here too. So those are the things that we need to determine, and the way that we determine them is we need to know what are the boundary conditions. So let's talk now about boundary conditions. So well, let's have a look at what the boundary conditions are. And so what we do is we require that the perturbations vanish on the boundaries. So in other words, that all the boundary conditions that are physical are applied to the first order solution, to the zeroth order solution, and then the perturbations themselves have zero boundary conditions. So basically we want U1 is equal to V1 is equal to W1 is equal to T1 is equal to 0, and the boundary conditions are Z is equal to 0 and Z is equal to D. So on the bottom and the bottom and the upper surface, the perturbations all vanish. We also need that d U1 by dx and d V1 by dy vanish at z equals 0 and z equals d. So that's going to be true. And that means that dW1 by dz is equal to 0 and z equals 0 and z equals d. Okay, so these things, dux1 and dvy1 being 0, that's implied by the fact that they're 0 at that surface, and then because of the incompressibility condition, then we also have this one as well. So we have it from there. Okay, so those are the boundary conditions. So the fact that that T1 is equal to 0 at the boundary. So we're going to look at what this one implies. So if T1 is equal to 0 at the boundary, then that means that we get a very complicated equation, a boundary condition for this function W. That looks like this: nu d squared minus a squared minus omega d squared minus a squared acting on W is equal to 0 at z equals 0 and z is equal to d. So the boundary condition for the function that we actually care about, okay, the function that we're actually dealing with, this function W over here. So that boundary so we know the boundary condition for W1. We don't know what the boundary condition for big W is, but now we've found it, and it's what I've written down on the right-hand page. So now I can expand what that is, and so I'm going to get this, expand everything out. I get d4w minus 2a squared plus omega over nu d squared W is equal to 0 at Z equals 0 and Z equals D. So imagine that you're Lord Rayleigh, and you're the first person in the entire universe to attempt this type of calculation, and you do all the work that we've just done in the last 2 lectures, and you get down to this equation, the one in purple on the left-hand side, and you look at that and you say, there's no way on earth that I'm going to solve this eigenvalue problem with this boundary condition. Forget it. So what you're going to do is you're going to do what we're going to do right now, is we're going to say, forget that boundary condition, we're going to make it simpler. So we're going to simplify the boundary condition. Now, that doesn't mean that it's correct. What we're going to simply do is just say, well, forget it. Let's try to understand the structure by making a caricature problem. So the basic idea.
Before we move on, can you explain again the boundary condition of the W again at Z equal to 0 and Z equal to D?
Mm-hmm.
How is that obtained?
Because I know what are the boundary conditions for because I know what the boundary conditions are for the other variables for T1 and so on. So then I know that at the boundaries, since T1 vanishes, then the boundary conditions for W is just determined by setting the equation on the actual equation as set equal to 0. So if you go back to the T1 equation, and then how far back I have to go to find that.
So this does not follow from the top equation that you have in.
No.
Oh, okay, yeah, okay.
Because the top equation is a 6th order equation, and the equation that I've written down is a 4th order equation.
Okay, I see.
Okay.
This comes from some previous equations, right?
Yes, it comes from this one. It comes from from this equation here, the one in the middle of the page. Okay, so all right, so what do we want to do? So what we want to do is understand the basic structure. By making a caricature, which is a very common thing in non-equilibrium pattern formation. You can't accurately solve the problem you want to solve, and so you solve the problem that you can solve. So by making a caricature with slightly different boundary conditions. So those boundary conditions are the following. We're going to say that W is equal to 0, D squared W is equal to 0, and D fourth W is equal to 0. And that's going to be true at Z equals 0 and Z is equal to D. So we're going to use those boundary conditions. And we want to use these boundary conditions because we know what the solutions are going to be. The solutions, when you have just, D2 W is equal to 0 and so on and so forth, we know that the solutions of that are going to be, harmonic functions. So we can see then that the solutions that have those boundary conditions are going to be of the form that W of Z is going to equal something like sine of n pi Z over D for n is equal to 1, 2, and so on and so forth. And so those will satisfy the boundary conditions, but they've also got to satisfy the original equation. So they've also got to satisfy the equation over here. It is right over here. So we have to satisfy that equation, and we have to satisfy the boundary conditions. And so if I assume that this is true, and then substitute that into equation star, then what I'm going to get is the following. So the solutions are equal that. These satisfy the boundary conditions. And equation star, as long as, now what you do is you substitute that in, and now you're going to get a constraint. And that constraint is going to look like this. Omega plus nu a star squared, omega plus kappa a star squared plus alpha g dt naught by dz a squared is equal to 0. So let me just write down what these things are. So A was something that we had to determine anyway from the equation for F. A star squared, by that I mean A squared plus n squared pi squared over d squared. And this is a quadratic equation. The thing that we want to get out of this equation is omega, the growth rate, and dt0 by dz, this term over here on the right. This term is just a constant. I've just been too lazy to define it to be something, but it's just the slope of the heat conduction. So it's just a number. So what we can do is solve this for omega. And so let me just write down the equation because it's just a quadratic. So solve for omega. And so that gives us this equation. And it's going to be a bit of a mess, but don't worry too much about it. I'll explain to you what it means. And then this thing is raised to the power 1/2. Okay, great. So that's the formula, and it's an awful mess. And so you're probably completely lost and wondering, so wait, what do we do with this? What the heck is this good for? And so the only thing that we care about is omega greater than or less than 0 as we vary. Well, what do we vary? Well, we have to vary the wave number, and the wave number is n pi over d, and we also have to vary the quantity A, because A is the physical wave number. So why is A the physical wave number? Well, just to go back, remember that we insisted that the perpendicular del squared in the xy plane satisfied this equation, and so that means that the spatial dependence in the xy plane, which is where we expect to see the rolls, that behavior is determined by A. So when we look at the pattern, let's see, somewhere over here we have a sketch of the pattern. Coming to it. Here we go. So when we look at the pattern, this patterns that we're looking at here on the left-hand side are in the XY plane. So the physical wave number that you're actually going to measure when you look at the pattern is going to be this quantity A. So we have to vary that as well. Okay, so now let's see what that gives us. So let's ask what happens then if the wave number is going to be positive. So for instability, what we need is that omega is going to be positive, or the real part of omega is going to be positive. So that clearly means that we need to have the plus sign in that square root. So why do we need the plus sign? Well, look at the square root on the left-hand side. You can see that what's inside the square root is greater than what's on the outside of the square root. So if you had the minus sign, that would give you omega is being negative. So the only way that you can overcome the this minus sign over here is if you have the plus sign over here. Okay, so we need that. So now then we have to ask ourselves, well, what is the condition that omega is greater than 0? And so what we need is that so for this to happen, what we need is that in the inside the what we need is that what's inside that square root has to be greater than 0. So what that condition means is that I'm going to just write it down, and then you'll see where it comes from. So what that means is that we need alpha G delta T over nu kappa D. That thing has to be greater than the term 1 over a squared into a squared plus pi squared n squared over d squared, that whole thing cubed. So all I've done is I've taken the formula inside the square brackets over here. I've replaced a star squared by a squared plus n squared pi squared, and then I've simply expanded that term and written it in this form over here. Okay, so what you can see now is that this is a condition on delta t. Okay, so what ultimately this is going to, hang on 1 second, please. Ultimately, what this is going to turn into is a condition that tells you how big a temperature difference you need in order for the system to go unstable. So let's now ask if this is going to happen, then I need to know what is the smallest value for this to happen. And for the smallest value for that to happen, I need to ask what is the smallest value of the right-hand side. So I'll come back to your question in a minute, whoever asked the question. Let me finish what I'm trying to say here. So the smallest value for delta t to give you an instability is when the right-hand side has its minimum value. And so we can see when that's going to be. So that's definitely going to occur when n is equal to 1. And then what about a? So clearly making n equal to 1 will minimize this term over here. And then we also have this term over here and this term over here. So now we have to find out what is the smallest value of a. And the answer to that, you can just differentiate and work it out. The answer to that is that a should have its value, its minimum value, AC, which is pi over d root 2. So all I've done is simply put n is equal to 1 in here and then found the smallest value of a. And so now I can take those values and substitute them back into the right-hand side. And so that then gives me that my condition is alpha g delta t d cubed over nu kappa has to be greater than the number I get by substituting all these terms into the right-hand side. And if you do that, it turns out to be 27 pi to the 4th over 4. And that's just a pure number. And so I'm going to call that pure number RC. Okay, so before I go on, I'll take whoever asked the question. Was it Daniel?
Oh yeah, I was just confused about where the cubed came from.
Well, yeah, I'm confused too.
Okay.
So I think what I did, so what I tried to do, so look inside that square root. So I've got an alpha star to the 4th, and I have an alpha star to the squared inside. And so what I wanted to,
right.
And so
it's only the term in parentheses that needs to be positive, right? Not the whole term in brackets.
Well, I need the whole term in brackets to be positive.
Doesn't it need to be not just positive, but bigger than the leading negative term in magnitude? Oh, okay. I thought it did.
I want to make sure that that term, I have to make sure that that term is real.
Oh, okay.
So I need to make sure that what's inside the square root is not negative. So I have an imaginary part. And then once it's real, and then it will automatically be greater than if I take the plus sign, it will automatically then be positive. So I think that's what I did.
Oh, I see. Okay.
Okay. So
Oh wait, no, I don't see. Oh, I do see. Got it.
Okay. How about this? We let that one go and you work it out afterwards. Okay.
Sounds good.
Okay. So it's just substituting in and looking for the condition for this thing to be real and positive. Okay. So that's easy to do. So this thing over here is a pure number. I've called this RC. So that means that this thing on the left-hand side is also a pure number. And that thing is called the Rayleigh number, after Lord Rayleigh. Okay, so what that says, let's look at the physics of this. So the physics of this that we've just discovered is that we can destabilize our uniform state in multiple ways. Okay, so way number one is we can increase delta t because over here on the right-hand side, that will increase this. I can increase D. I can increase alpha, the thermal expansion coefficient. All of those things will cause the left-hand side to increase and potentially go above this magical number of 27 pi to the 4th over 4. The other thing that I can do is I can decrease nu, or I can decrease kappa. So doing any of these things will increase the left-hand side and eventually cause the uniform state to become destabilized. And of course, if you're going to do this in an experiment, the most sensitive variable that you would vary is D, because it's the most highest power. Right. So if you make a small change in D, that gives you, a cubic power rather than say just increasing delta T. And the other thing you can do is you can make nu very small. So when you do experiments like this, when you try to get up to Rayleigh numbers of order 10 to the 13, 10 to the 14, which people can do these days, they do it also by using uranium hexafluoride gas, which has a very low viscosity and various other material properties and so on. So there's various things that one can do to make the thing destabilized. So we can also think of this in the other way around, which is what stabilizes the system. So the other thing is that we can say is that increasing nu or kappa stabilizes the system. And they both come in the denominator of this Rayleigh number. So nu comes in because if you make the system very viscous, then it's going to be very hard for the fluid to start moving because it has to fight against the viscosity. Similarly, if you increase the thermal conductivity, then you don't get those hotspots developing, just like in the lambda transition of superfluid helium. And so again, that stops the formation of these convection patterns. So that is the prediction, and so this prevents easy flow. And this prevents hotspots. Giving buoyancy. Okay, so we can see then that there's two numbers that describe this system. So in summary, patterns form when the Rayleigh number exceeds a threshold. And you can work out more precisely what it is. That threshold is RC, which is about 1700 from experiment and from a more detailed calculation. This number 27 pi to the 4th over 4 isn't so bad. So we've got something about the phase diagram. It also depends on nu and kappa, and so we have another dimensionless number called the Prandtl number, which is usually written as PR, and that's just the ratio of nu over kappa. Okay, so from this, we can now construct a phase diagram. And what I want to do next is to talk a little bit about what kind of patterns we get, and then ask another question: how stable are those patterns themselves? So we're not going to do this today. We're finished with today's lecture. But the next thing that we're going to talk about in the lecture is what are the patterns? What is the phase diagram? And are the patterns themselves stable? And the answer to the last question is they're not stable. They're stable within some range, but then as you start to increase the Rayleigh number, then you get a whole succession of instabilities, ultimately giving rise to fluid turbulence. Anyway, so we'll talk about all of that next time. That's the end of today's lecture, and in fact, because this is the last in-person lecture, so the remaining lectures, the makeup lectures, I will record offline and post them, and I'll let you know when I've done that. So this will be this is in fact the